the Department of Educational Psychology, Leadership, and Higher Education. She holds a Ph.D. in educational psychology with an emphasis in assessment, quantitative analysis, and a graduate certificate in online teaching and training, a graduate certificate in program evaluation, and a graduate certificate in teaching. She is the assessment coordinator of the College of Education undergraduate seminar programs, and she teaches these as well as graduate level research courses. In addition, she provides faculty research and data analysis support for the Office of Learning Analytics. Dr. Wolff's research focuses on self-regulation, motivation, measurement, and the integration of mindfulness in educational settings. She is particularly interested in the dynamic processes of modeling with in-person variability over time. Her methods expertise include psychometrics, structural equation modeling, and intensive longitudinal designs. Today, Dr. Wolff will deliver her presentation with an opportunity for questions and answers at the end of the session. So please join me in welcoming Dr. Wolff as she discusses modeling complexity and motivation, a within-person approach with lag1 graphical vector autoregressions.
Thank you so much, Allie. And I know that's quite the mouthful, but hopefully by the end of the day, we'll all kind of have like a fairly decent understanding of what lag-1 graphical autoregression is and what these models look like. I'll apologize in advance if I sound like a 14-year-old boy. I was sick all weekend, so I've lost my voice. It's cracking. I'm going to do my best to kind of sip on my tea during this and move through this so that we can get to some data sharing. So without further ado, let's just jump right into it. Hopefully everybody can see my screen all right. There's a lot of motivation for that we feel as a field for like within person modeling. I'm not going to kind of talk about this too much. I think most of us in the complexity world are sort of on the same page with this kind of thing, but the idea that these processes, especially motivational processes, they unfold within individuals over time. So they're very nonlinear, they're context sensitive, they're often recursive things. And we've been researching in the Office of Learning Analytics here at UNLV. I work with an amazing team, and we've been kind of thinking about motivation in terms of feedback loops of being concordant, kind of in line with some kinds of concordant cycles of motivation, or being negative, so disruptive, or decoupled, so kind of fragmented. And so the core sort of question behind all this is kind of how does motivation sustain itself over the semester, right? Or how does it destabilize within students? General longitudinal models, for different kinds of things, including self-efficacy, are fairly insufficient at capturing complexity, make a lot of assumptions about that don't necessarily capture that motivation is something that's dynamic, it's evolving, it's not fixed, it fluctuates across time, situations. The past experiences shape our future trajectories. Success, right, can build confidence and fuel persistence, while failure can do things like discourage further effort. These kinds of self-reinforcing cycles, what we would call concordant cycles of motivation, are really difficult to model. Context also really matters. So the same person might feel highly motivated in one context, but not in another. And then there's, of course, individual differences, and motivation is certainly intertwined with kind of everything, thoughts, emotions, behaviors. Yet here we are trying to measure it. So we need context specific kind of like dynamic sensitive methods that go beyond static. I really, really love this particular kind of image, this kind of figure, as a way of explaining why within-person modeling really matters. So you're looking at this cube, right, where every little cell represents one data point, essentially a single individual measured on one variable at one occasion. And so along the axis, we have individuals, and then along another, we have the variables we're measuring. So things like maybe competence, autonomy, relatedness. And then along the third axis, we have measurement occasions or time. In most traditional studies, we collapse the cube in some way. So we might average across individuals to get overall means. We might look at 2 or 3 time points across a semester or do a combination of those things. And it tells us how students differ on average from each other, but doesn't necessarily tell us how students' motivation changes and interacts over time. When we keep the cube intact, when we try to keep that cube intact, we repeatedly measure the same students across multiple occasions, and we start to see the patterns within the individuals, how one variable at one time point predicts another at the next time point. So the cube really represents the foundation for any within-person approach. Instead of flattening the data, we kind of try to keep all three dimensions. Now, traditional sort of structural equation modelings, we're kind of starting to ask different questions when we shift into different modeling techniques. Within-person perspective, we're trying to ask not who's more motivated, right, but how does motivation evolve inside a person from one occasion to the next. To get to the lag1 multi-level graphical vector autoregression, it's really helpful to think about kind of where we're coming from. So a lot of us are trained on structural equation models, maybe cross-like panel models, and these are super powerful for testing directional paths between constructs, like autonomy predicting competence or competence predicting autonomy, vice versa, those things predicting achievement, right? But these models are built on some pretty strong assumptions, treating relationships as stable across people over really long intervals and limited to most of the time, for power reasons, to kind of relatively few time points. They show us these like average trends, but not how they interact again within an individual. This is kind of where the network models come in. So instead of pre-specifying sort of one directional path, we're going to estimate a web of conditional dependencies, how each component connects to others in real time. The model that we're ultimately going to look at today, the lag1 MLGVAR, which is how I'm going to say it from now on so I don't stumble upon my words, builds kind of on this idea. So it combines time series modeling with network estimation to capture short-term feedback loops within individuals. And this sort of advancement is fairly recent. A lot of this comes out of the University of Amsterdam, Sascha Epskamp being sort of one of the people who's sort of pushing this forwards, and sort of surfaced in 2019, 2020. And we're sort of like, I get that it's dynamic, it's network-based, but what does the model actually do, right? So the logic is fairly simple. We use each variable's value at the previous time point to predict all other variables at the next time point. And that's the lag1 part. It's multi-level because it separates two sources of variation, differences between students and fluctuations within students over time. The model will end up estimating three distinct but related networks: the temporal network, contemporaneous network, and the between-person network. And we're going to talk about those more soon. And then what we get is kind of a visual output where we can see these conditional dependencies operating within a network among variables over time. And then that's how we can see both the system structure and its movement, so how it stabilizes or destabilizes in real time. So to build towards our understanding of this particular model, I'm just going to like really quickly introduce these things in case you're unfamiliar. So, and kind of what it adds to our model and kind of where we're going. And sorry if I'm moving kind of quickly. I want to make sure we have time to sort of look at some code together. So first is the Gaussian graphical model, and these figures are really helpful. I borrowed them from, this one's borrowed from an Epskamp paper. I'm going to give you a folder that has a lot of really amazing resources from some of these authors, in addition to my slides and some code at the end of the presentation. So we start here with the Gaussian graphical model. It's just a way to visualize a web of conditional dependencies among variables, even for controlling the others. So this is still static, but it tells us structure, not change. So this is a network representation of a multivariate Gaussian normal distribution, which is a bit of a mouthful, but essentially it shows us which pairs of variables are statistically related after controlling for all of the others. We start with the covariance matrix, which tells us who moves together, and we invert it to get the precision matrix, which tells us who is uniquely linked. And those entries are what become the edges in the network. So the blue or the red line that you see here, the thick blue means two constructs rise and fall together even after we account for everything else. If there's no edge between them, it means they're conditionally independent. And if it's red, that is showing us that they work inversely. So the GGM is what gives us the static picture of the system structure, who connects to who, but not yet how those connections unfold over time. So some of you will probably be familiar with an AR1 model. We're going to kind of try to add time in here. So an AR1 model simply says today's value predicts tomorrow's value, and that gives us a kind of like inertia, or how stable the process is from one occasion to the next, whether it builds, whether it drops. And once we know what's connected at a single time point, the next question is how stable is it over time? So the autoregressive of order 1, it adds a time dimension, predicting each variable from its own value at the time before. It gives us autoregressive coefficients, and conceptually it tells us how much, like how, in this example, how tired we were yesterday, how predictive is it of how tired we are going to be today. If it's a low value, right, that's kind of instability, maybe some volatility. The construct maybe changes rapidly from one occasion to the next. If it's a relatively moderate value, or maybe an increasing value, it's going to tell us that the process is stable, or maybe it has like an inertia quality. So this answers the layer of how, if we're thinking about motivation, like how persistent are motivational states within a person over time. To model, it's still treating each variable in its isolation. And we know that motivation isn't an isolated process, right? So to model those cross effects, we move towards vector autoregression. So our little diagram is getting a little bit more complicated here, right? So in the AR1 model, each variable only predicted itself. In vector autoregression, essentially keeps those self connections, but lets each variable at the previous time point predict every variable at the next time point. So you can see all these sort of crosses in the model here. Say we've got like feeling tired, but then how much we exercise, right, in this image here. So each variable is predicted by both exercise and tired at the previous time point, at the next time point. So that's the standard vector autoregression, where we're modeling how variables predict each other across these lag 1 effects. The residuals, though, are still correlated, and those residual covariances represent what's happening within the same time point. So variables that rise and fall together at the same moment after we account for lagged effects. To visualize and kind of regularize that complex system of crosslinks, we move from this kind of vector autoregression to the graphical vector autoregression. So we're kind of adding back the GGM part. So when we get here, we're starting to merge the time series logic with network visualization. So again, in the vector autoregression, we're estimating kind of a big set of regression equations, all the cross-lagged and autoregressive coefficients. In the GVAR, we turn that system into a network by focusing on unique connections and not necessarily raw predictive strength. Technically, that means we convert some of the coefficients into partial correlation. So every edge in the network represents a direct conditional dependency after controlling for all of the others. And it makes the structure more sparse and more interpretable, so we can actually see the core feedback loops that might be present in the system. It takes the residual structure and turns it into a network, so separating the temporal and the contemporaneous components. So the temporal network is showing us how states influence each other over time. And essentially, these are the directed lag 1 effects. So these are those regression coefficients. The contemporaneous network captures the same time co-activation among variables after we've controlled for those lagged paths. So this is what you see kind of below, the second image below. The highlighted residuals here are what's represented in the contemporaneous network. It tells us which constructs tend to rise and fall together at the same time. So in this case, if we're looking at this particular network being sad and tired, we would interpret this as like, while I'm sad, I'm also feeling tired. Whereas above this in the temporal network, we can see something like if we're looking at tired and it has this nice kind of autoregressive loop on it, this is when I'm tired, like I'm going to be more tired tomorrow, right? Because I'm tired today, I'm going to be more tired tomorrow. So the edges are we can think of the edges in the temporal network still along the same lines that we would think of regression coefficients. In the contemporaneous network, we think of them as partial associations. And they're typically regularized. We won't get into the super techy details here because I just don't possibly have enough time. But regularization, like an Ebbitt lasso, it essentially will shrink weak edges towards zero, leaving only the strongest kind of most reliable couplings. So together, these networks show not just who, or rather what's connected, but how those connections evolve dynamically. And if we're thinking about a motivational system, that means we can actually start to visualize things like feedback loops reinforcing each other, or maybe a breakdown in competence forming kind of some kind of disconcordance, or that, and how those things relate to maybe disruptors of motivations like withdrawal and tension or academic burden and things like that. So now, if hopefully we're all still there, but we're going to move on to our multi-level lag1 GVAR now. This is extending the previous model to nested data, so repeated measures within students. The difference is it decomposes the variance into between and within person parts here, and then estimates 3 networks. So we get the temporal and the contemporaneous network still, but then we also get this between person kind of, say, stable traits. And this is the framework that we've used to kind of model motivational dynamics. The model itself recognizes that our data aren't just long time series, but they're nested, right? So they're nested with observations within individuals. If we simply pooled everyone's data, we'd mix 2 kinds of variation, right? How students differ from each other, and then how motivation fluctuates within the same student over time. So the MLGVAR disentangles these. The between person level network is kind of trait-like covariation. So students who are maybe generally high in confidence also tend to be high in autonomy, right? If we're thinking about self-determination variables. The within person level, we have two networks, the temporal network and the contemporaneous network. Again, that temporal network is describing state lag1 influences. So maybe how one variable predicts a variable at the next time point. And then the contemporaneous network is showing same time co-activation within a certain time period. Technically, we get kind of 2 distinct covariance structures here instead of one pooled one, which is the difference between the previous model. So the covariance matrix is decomposed into between and within person parts. And then we apply the same logic of the GVAR to the within person covariance matrix and between person covariance matrix. So at the within person, we fit the same lag1 GVAR equations as before, but now on its own within person covariance matrix. And on top of that, we model relationships among person level means. And that gives us the kind of undirected between person network. The result is pretty cool. We kind of get like a very cool picture of our variables across time. And then we can think about these kinds of questions that we might be asking. So for the temporal, if a student feels confident today, are they more likely to feel a sense of something else tomorrow? Maybe that's relatedness or whatever your other variables are. Contemporaneous, while a student feels confident today, are they also feeling a sense of relatedness today? Between people, do students who are generally more confident also tend to have a higher sense of relatedness? And that's the question that is answered the most kind of amongst our research in our field. And so by kind of breaking this down, we get this 3 levels of the system: how it looks as a trait, how it kind of co-activates within a certain time period, and then how it changes from one time period to the next. So this is what a temporal network kind of might look like here. So each edge is corresponding to a model parameter, either a standardized regression coefficient or a partial correlation, which would be the contemporaneous network. In the package psychometrics, which we'll use in R, we compute standard errors and p-values for each one. And this gives us kind of solid lines indicating parameters that are statistically significantly different than zero at the threshold that you set. Dashed lines are going to say that they're non-significant but still present. If there's kind of no line, that means they're kind of sort of more like zero, like kind of independent or showing up as independent. This is a pretty complex multivariate model. So small non-significant edges, they may still have interpretive value if they're kind of consistent across contexts. But we're going to sort of focus like our discussion and things on the stable significant ones. There's ways to sort of run bootstraps of these models to sort of see if your edges are repeated over a bootstrap sample. And that's something that is sort of the only validity check on these models at the moment. And something that I'll provide you some like documentation of how to do in the resources that I give you. So I think it's really important to sort of, before we move into like looking at the model itself in R, kind of thinking about what it can show us and what it can't, right? So it reveals conditional temporal dependencies, right? So how changes in something at a previous time point predict the changes at the current time point after controlling for all of the variables in the system. It gives us the direction and relative strength of those lag one effects, which lets us map a kind of feedback structure. It also shows us how constructs relative stability through its autoregressive edges, because how much a variable carries over from one session to the next. These temporal edges, though, they don't prove causation, right? They show statistical direction, but they don't show experimental control. The model assumes linear lag one relationships, so it won't detect nonlinear dynamics unless you've taken that into account when we've treated our data before we've started this process, which I'll talk about when we talk about assumptions here. It also doesn't capture unobserved like latent variables that might drive multiple nodes or person-specific heterogeneity. So when we interpret these networks, I like to read them sort of as maps of short-term coupling among observed variables, not necessarily as full causal symptoms. And that distinction kind of helps keep inferences strong, but like necessarily cautious. This is not right idiographic, right? So it's group level aggregation. So on to our assumptions. We have some key ones, right? Key stationarity, the assumption that our means are stable over time, that only adjacent sessions predict the next. So we're not talking about higher order relationships here. We're talking about lag one relationships. If some effects take longer to manifest, the lag one model will either underestimate them. So if there's lag two or lag three relationships present, our lag one model will either underestimate them or kind of absorb them indirectly into our contemporaneous or autoregressive paths. We assume a Gaussian multivariate normal assumption, which can be really easily mitigated with non-paranormal transformations. Most of the time we don't end up with nice, beautiful multivariate normal distributions in our data. You need sufficient time points per person for this. Interpreting those edges again as conditional dependencies, and that meaningful lags make sure that we have lag one dependence. So we're going to talk about these assumptions a little bit more in detail as we move to like this applied example. And then I'm trying to get us so that we have 15 minutes to spend in R and kind of play around with this code. So this is an applied example. It's a paper that's under review. This is study 2 of this paper. And we did something a little bit unique in the second study of this paper. Hopefully this is under review with JEP. So hopefully this will be published in the next 6 months or so. We'll see. We're to set the stage, we're talking about self-determination theory in this paper, and we're thinking about these things as dynamically interacting to sort of sustain motivation over time in general. I'm going to speed through this, like the theory part, so we can kind of get to the more technical stuff here. Um, we're thinking about sort of conceptualizing what a concordant cycle of motivation would be, thinking from like back through Sheldon and Elliott and what they were thinking about as concordance in relationship to goals and personally meaningful learning. So our main questions that we have, though, the main question we wanted to explore is, does instructional context alter the organization and interdependence of students' motivational systems, including any associations with a disruptor of motivation, like a sense that they want to withdraw? Our hypothesis was that students who are participating in one form of the curriculum, which was in this kind of inclusive discussion-based pedagogy, a very specific sort of not your traditional class type, that they might show more coherent reciprocal motivation when they're in those classes versus when they're in the traditional lecture-based classes. We're talking about the same students in kind of alternating contexts within the same class. And so how the study is set up is we've got, in the 9, we measured the students with the same measures kind of every day they were in class for the whole semester. This inclusive discussion curriculum was called Touchstones. And then we have the kind of non-touchstone settings. Within the 9 weeks, kind of towards the middle of the semester, they had 2 classes. One of those classes in the week would be the Touchstones class, and then the next class would be a traditional lecture style class. Same instructor, same students. So they kind of alternated over 9 weeks. And so we had 18 measurements over 9 weeks for these students. So we wanted to compare within-person motivation, the dynamics of the within-person motivation for these students across these contexts. And so that's why this sort of lecture is titled like a within-person approach, because we're sort of taking like an ABAB sort of design here, and we're going to kind of map the networks of the same individuals only for the days that they're in the Touchstones class versus only when they're in the traditional lecture classes. So we're modeling separate LAG1 MLG VARs for each context. And that would frame it so that differences in the structure are going to reflect that contextual change, and so not different students. So that's really key to kind of understand as we move forwards. We had about 442 students. We had a bunch of sections, a bunch of instructors. Again, there was 9 classes where they were doing the kind of touchstones classes, and then 9 when they weren't. Our hypothesis, again, was that we were going to see more concordant motivation, more connected motivation in those touchstones classes, and that we were maybe going to see either negative things or just more fragile systems in the non-touchstones classes. We established kind of scalar invariance and reliability for all of the constructs before we move forward. This is just an example of some of these items. I'm just going to speed past this. You'll have a copy of this, but let's get a little technical on what we did to meet our assumptions for these models. So we made sure that we had true multi-level structure. So we needed to calculate ICCs to make sure that we weren't having instructor effects, things like that. We tested scale invariance. We didn't have any sort of indication that we had patterns of missingness that were violating, our assumptions of MAR. Psychometrics, this should say psychometrics, not psychometrics. Psychometrics expects a complete covariance matrix for long format data right now. And we imputed the data via MIS for us, therefore. So this is sort of something that I've been told that they're working on. There's other aspects of the psychometrics package if you're doing a slightly different kind of analysis that you can use FIML to handle missing data directly through psychometrics. However, that's not currently the case for what we're going to show you today. So we had to have a complete data set in order to run it. So we imputed, which is something we've been doing with these data already. So we imputed using Miss Forest. And then we made sure for our multivariate normality assumptions, we applied a non-paranormal transformation using the huge package in R. And that approach rank orders each variable and maps it onto a Gaussian distribution while preserving kind of the monotonic relationships among the variables. So this is like fairly helpful when self-report scales have ceiling effects, which is pretty typical. And after transforming them, we checked for kind of mean and variance drift. And that would be where we're looking at stationarity. We did find some like significant linear trends, and to correct for that, we detrended the variables using just a simple linear regression of the variable on time and then saving the residuals. So in other words, we subtracted each student's best fitting linear trend so that the resulting series reflected only the session to session fluctuations around their expected path. And those residualized scores were then used in the MLGVAR estimation. And this is really common in this kind of analysis to do. So here's just our results here. We have the within person. Again, these networks were estimated within people, but they're separate networks for classroom context. We've got the Touchstones discussion class over the top and then the non-discussion class in the bottom. This is the same group of students measured repeatedly, kind of alternating between Touchstone discussion days and non-Touchstone instruction days. In the Touchstone, you can see this blue, the solid lines. We get this kind of positive feedback loop from between competence and autonomy. And so when students are feeling more competent, they're feeling more autonomous in the next session and sort of vice versa. So it's kind of feeding itself. And then we also see that like competence feeding into relatedness. And all of these have like autoregressive paths that are all significant. So they're feeding themselves over time. The system is kind of overall, we would consider this like these paths are relatively stable because they're significant and they were fairly, I guess I wouldn't call them large, but they were large enough to kind of show up in our model consistently and over lots of bootstrap samples. And in contrast, in the non-discussion classes, what we see is that competence became a lot less stable over time, right? So that kind of broke down. And then it began to couple negatively with a sense of wanting to withdraw. So this is like a discordant loop, right? So autonomy and relatedness are autonomy and competence are that cycle got broken. The system showed fewer positive links overall, right? We only have 2 significant kind of positive links between variables. And again, this is about the same group of students, how their motivational system behaves differently in these different instructional contexts. And the takeaway really was that not that necessarily these discussions cause motivation to rise, but they appear to strengthen like this short-term coherence among the motivational processes. Whereas these traditional contexts may temporarily weaken those couplings or maybe allow this like disruption to sort of emerge in the system a little bit more clearly. Which we found super interesting. And the contemporaneous and between person networks, you can notice they look kind of fairly similar, and there was nothing sort of too concerning or strange that we when we were looking, or too wildly different. And so what this is really telling us is that by kind of focusing on parsing out, right, in the multi-level structure, we're parsing out that between person variance, and that allows these sort of temporal differences to emerge. So I want to move to showing you all in R some of this stuff, which I call the fun part. So I'm going to go ahead and get this set up to share with you all. Bear with me for one moment. I had a little weird hiccup right before all of you came in here with the data, but we was able to get it sorted. I just need to pop it into the drive for you and then I'll share it.
Yeah, this is great, Sarah. I'm so happy I got to watch you instruct this or give us this demonstration today.
Oh, thanks, Lola. Shout out to all the UNLV folks who showed up in support today. That was very sweet. Well, I'm going to leave some time for some questions here at the end too. So bear with me for a moment as I uh, get this set up for you. All right. Great. All right. Perfect. Okay, so I'm about to drop a Google folder for you all in the chat. This has the slides from today. It also has the data and the code that we're going to walk through here in just a moment, and also some other things in here. I've got a really cool PowerPoint from Sasha Epskamp in here that kind of goes into the psychometrics package itself, the psychometrics manual. The code book for the study is in here too. And then I think there was one other thing I stuck in here for you, one other resource. Nope, those are the two things. Um, all right, so I'm going to open up if you're following along with me, that would be also great. Okay. Sorry. All right, here we go. So the network code, let's see. Oh, I'm not even sharing my screen with you all. Bear with me. Where did my Zoom go? There you are. Okay. All right. So hopefully you can all see this. I know it's kind of hard to follow along unless you have it open on your own, but you can always play around with this later. Um, so just looking through this code, of course, we're going to load all of the packages, and if you don't have them, you can always install them. You shouldn't have any issues there. You can just close the study one tab because you don't have the study one data, and we're looking at study two right now. So the first part of this is reading in the data and kind of setting up the data set. You'll see that if you kind of run all of this in bulk, that's kind of setting us up with how the data preset order is the time variable in the data set. We're going to rename it to time. We're going to kind of condense the data set to only conclude the items that we're going to be running. We're using the means for the items in here, and that's calculated here. And then we're going to move forward with building a second data frame that just has the ID, the time variable, and the 4 variables that we want to use, and then subsetting that to only include the time points. Remember, there's 30 time points in this data. We're looking at the kind of middle 9 weeks where they were doing this touchstones, non-touchstones, kind of alternating context. The first thing we do to this data is we transform it using huge, and then we're going to add it back into the data frame. And then here's where we're going to check if that data is stationary by running these kind of simple regressions. And you'll see that in our data, we kind of always have like a little bit of an effect of time. And so I'm going to save a little time to get to the psychometrics part here. We're going to run through all of this. We're going to detrend them by saving our residuals from our models and adding them into the data. So that's what this is doing here. And then we're going to select the variables that we save in an object called vars, because that's how psychometrics kind of likes to handle it. You can type them all in, but I found it's just easiest to do this, save an object with the variables that you want to use. And then here we need to separate touchstones versus non-touchstones, and that's what this is doing. So we have touchstones data and we have non-touchstones data. We're going to run two models. This is the model command, and this is where we are kind of setting all of the information that the model needs. So you can see that, again, we're using a FIML estimator. However, because of kind of a hiccup in psychometrics right now, like I said before, if you're going to try to run this and it has missing data in it, it's not going to like it if your data is in long format. There's ways to run it in wide. I think it's a little bit more complicated. We had imputed these data already, so this is our imputed data set that we're using, so it doesn't really matter. It's the MLTSL LVGVAR function, and within that, we're naming our data sets. BeepVar is how we're designating what is our variable of time. We've called it time, so that makes it easy. If you have one that's day or week or hour, I don't know, whatever your time interval is. Then we have an ID variable. We're naming our variables, which again, we saved in an object called vars. And this is just saving this as a model object. So we're saving it as an object. And then we're doing a second model object, that's model 2, that we're saving, that's using the non-touchstones data. And I think I see, how did I merge the imputed data sets?
You can tell me later. It doesn't need to be right now.
Yeah, no problem, Lola. We can. So now we're going to be using psychometrics itself. The model commands are really, really simple. So this is telling us to run the model here. And you'll see that we got a little warning. And this warning is actually not so bad. It's like not as scary. It's a don't panic warning. It's a really common warning message. So the optimizer encountered at least one non-positive definite matrix and used a pseudo-inverse, and that's what it's supposed to do. So it simply means that during the estimation, one of the intermediate covariance matrices wasn't perfectly invertible, and typically that's because of small collinearities or maybe some near zero residual variances, and it happens a lot in multi-level and nested data, especially with highly correlated variables like motivation variables. Or when there's maybe some limited within-person variability. And so this optimizer is automatically handling this by using a pseudo-inverse, basically a mathematically robust way to approximate the inverse when the matrix is almost singular. So as long as the final parameter estimates make sense, we get the kind of expected signs and reasonable magnitudes and model fit, this warning isn't totally a problem. It's more of a diagnostic note than a sign of model failure. And I've always gotten this like warning whenever I run these models. So if this happens to you, don't freak out. This is not a freak out, a freak out one. So we run model 2, you'll notice, oh, we got the same exact model warning. And again, we've got touchstones is mod and non-touchstones is model 2. We can look at our model fit. You can see it spits out kind of a multitude of fit indices for us. Some of them will be more familiar than others. I actually had been exchanging some emails with Sasha Epskamp not too long ago that they were working on a simulation paper to kind of decide what these model and fit indices truly mean in this context. Right? We're kind of used to just like saying, oh, does it fit by the general sort of heuristics of, is it like higher than 0.9, et cetera? Is our RMSEA relatively lower? And we have sort of reasonable fit here. We have AIC, BIC values. All of that is given a chi-squared value, all of that. Hopefully that paper will come out soon so we can all reference it when we're thinking about these models and what fit actually means. We can look at model 2's fit here. Again, if we're looking at traditional fit indices, we're looking pretty okay, nothing crazy. And then we can look at individual parameters by sort of just calling this parameters command. And here we're looking at all of the different matrices, right? So when we want to look at the temporal sort of network, we're looking at the beta this beta matrix, right? Your variables are going to be labeled not kind of in the order that you designated them in the vars command. So variable one is the first variable in that order. If we're looking up here, right? Variable two was aught rel within withdrawal intentions. And so just keep that in mind when you're doing your interpretations. We get a p-value, a standard error, sort of all of the things we would expect to get. I like to extract the matrices in a way that like helps me graph them more. So this command here is extracting all of the relevant matrices. So our beta matrix is for our contemporaneous, our between network is represented by our omega zeta between, and then our contemporaneous is our omega zeta within. So I'm just extracting all of those and saving them as objects. And then I'm going to kind of move down here to, if you want to extract marginal contemporaneous correlations or between subject covariance matrices, that's what this code does. I'm going to kind of skip down here to our graphing. And to graph, I'm going to set these sizes and margins and things to graph my PDF. So it's going to give us a layout where we have all three next to each other, and it's using QGraph, and so that's why we've loaded QGraph in here. You can specify kind of what like some things to change, whether you want, what kind of significance value you're looking at here, and a few other things. This is all spelled out really clearly, fairly clearly in the QGraph notation. If you kind of look at the manual in R. Here, if you were just to copy paste this on your own, you wouldn't have to really change. As long as you used the vars and labeled your own variables in the vars command, you wouldn't have to change any of this. You could just truly just like copy paste this code and make your own graph. So it's going to, if you highlight and go through all of this, it's going to plop the PDF into your own folder. And it's that PDF pops up in the Google folder that we have already open. It should just automatically save as a PDF. It won't pop up in R. It'll pop up as a PDF outside of that. Okay, that was like a total whirlwind, and but I wanted to leave a few minutes at least for any kind of outstanding questions at the moment that I might be able to answer.
Sarah, great job. I have two questions.
Yeah.
You said that it's possible to model non-linear relationships or non-normal distributions or both.
Yeah, so you can transform your data to approximate that Gaussian multivariate normal. That's an assumption of this model itself. So you can model you can model non-normal data if you transform it to approximate a normal distribution, right? Now to your second question of can we model nonlinear relationships? So and you're a SEM person, Lola. So MLGBAR is fundamentally kind of like a linear Gaussian SEM. So nonlinearities are just not estimated directly. They can be incorporated. Obviously, they can be incorporated when you add transformed variables. Maybe you could do something like quadratic or cubic interactions, that kind of stuff, where you're sort of like adding that into your variable model and including them as nodes. Maybe piecewise or threshold type variables too. Or you can maybe fit separate networks for different sort of segments of your data as well.
Okay.
But the model itself is not really well equipped you'd have to kind of do
Yeah.
some jumping through some hoops.
Yeah. Not all models for everything. My last question is, how did you handle the imputed data?
So I'm happy to share this with you, Lola. I have a piece of code written that essentially it goes through, it uses the Miss Forest algorithm, the Miss Forest passage, package in R,
Right,
and it goes through and I generate 50 imputed data sets and I choose the
right.
one with sort of the lowest error value. And I have a function to do that. And I can
But
share that with you
when you have imputed
or
data,
anyone who wants to email me.
I was just wondering when you have imputed data sets, don't you have to preserve the between data set variance? It,
Yeah, so the Miss Forest algorithm, if you've never used it, it's
I
actually
haven't.
pretty awesome. So I'd be super happy to kind of go into more detail with that with
Okay.
you, Lola, but I do want to give everybody a chance to ask about MLG bar right now.
Okay. Sorry, I'm hogging your time. Thank you.
That's okay. Any other questions about this particular model?
I have a question about the interpretation. Do you mind going
Yeah.
back to the original slide deck on page 11? You were talking about the way that you were talking about the interpretation of the data. I just want to understand something in relation to, I think, the prior comment, the way that we interpret nonlinearity or linearity and directionality.
Slide 11, you said?
Yeah, I think so. I'm not going to be able to remember the exact language you used, but I'm hopeful that you can help you recall what you said.
Yeah, yeah, let's see. Let's go to slide 11 here. Uh, um, in thinking about the interpretation of like in what particular network or any network or
Do you mind sharing your screen so I can kind of
yeah, yeah, yeah.
join you there? Thank you.
Yes. Sorry.
No, you're good. Thank you. So you were saying at one point something like if someone is tired, that feeling sad, the
Yeah.
if you're tired one day, then we could predict that they would how that would make them feel sad. Some of you said something about one of these relationships. I just can't remember exactly the language you used, and I have questions
Yeah.
about that interpretation.
Yeah, so for this like temporal sort of network here, if we were looking at like tired has like this strong autoregressive effect. So it's like if I'm tired like the day before, like I'm like gonna be tired the next day, right? So it's saying it's like how you would interpret sort of like a normal autoregressive effect. Um, and that's taking into account all of that's like taking into account all of the other variables that are present in the network, right? So that relationship still exists when you're thinking about how relaxed and nervous and bodily discomfort and rumination or whatever the other variables are in this list. The contemporaneous network we can think of as a while, right? So while I'm sad today, I also feel tired today. And so I think that like that helped me a lot when I was first kind of trying to like wrap my head around what the difference was between these two within person networks is like we've got the autoregressive sort of lag one network is the temporal network and that's separated from like this feeling of like wow, and this is represented again by what's highlighted here, these the residual, it's the inverse matrix of these residuals between the variables, right? And we're looking at, obviously, we're looking at kind of a whole bunch of other like cross lags here because we've got like relationships between all of these different variables being estimated. Does that make sense?
Yeah, it makes a lot of sense because I think what the way it was phrased, at least the way I interpreted what you said earlier, was it seemed like if tired, therefore sad, and now it seems like no, these are co-occurring and they're
Yeah,
merging.
it's
Yeah,
covariation. So it's
co-variation.
while
Yeah.
I'm
Okay.
tired,
Yeah. Yeah.
I'm also sad.
Great. Okay. Thank you.
Yeah,
This
no
is
problem.
awesome. I love all this. This is an amazing presentation. Thank you so much.
Yeah, no problem at all. Here, I should put this up. There were a few other slides that just have some like information on psychometrics itself, the package. You all have access to that now, though. I sort of tried to talk through those things while we looked at the code since I was running out of time. Um, but yeah, I'll put my email up here as well. Any other questions at the moment? I think Ali maybe wanted to make an announcement before everyone left as well.
Yeah. Well, first, thank you for the rich presentation and sharing all of these wonderful things within Google Drive. I encourage everyone to reach out to Sarah if you have further questions. Um, and then if I can share my screen real quick. Our next webinar series we have coming up will feature Dr. Brennan Schutz, where he'll discuss formalizing complexity theories with systems, dynamics modeling, examples from self-regulated learning theories. And then lastly, we still our applications for our Sprint mentorship program are due in 3 days, 2 days, Friday. So if you have any interested graduate students, or if you would like to mentor a student, please follow the links. This program will run from January until AERA. And if you have any questions, please feel free to email me. And then lastly, make sure to like and follow us on all of the socials so you can stay up to date with all of the SIG offerings. Yeah, and we're at 1 p.m. So thank you.
Awesome.
Thank you, Sarah.
Yeah. Yeah, and please feel free to email me. I'm always happy to like jump on a Zoom or something if you're working on network model that I can help with. Um, these are things are like relatively new, so like I've wrapped my head around them in the last couple of years. I think it's all super cool. So I'm always super happy to bounce ideas back and forth.